So I think today we'll start the session now. Good afternoon, everyone. Myself Adyasha Sahoo from Department of Electrical Engineering, IIT Roorkee. So today we will be discussing regarding the week 5 of the course Smart Grid Basics to Advanced Technologies. So first, obviously, we'll go through the overview of this week, followed by some question and answer session, and then we'll go through the doubts if you have any. These are some of the links if it is required by you. The slides and the video are available in the Google Drive and videos. So in this week, firstly, we studied regarding microgrid. So can anyone would like to first unmute and share their views, and then we'll talk in detail. What is this microgrid and why this scenario is coming up now? Okay, so basically this microgrid is a localized energy system. So it can work independently or it can work in coordination with the main power grid. It is basically a small localized system consisting of various energy resources such as solar panels, wind turbines, batteries, traditional generators, along with sophisticated control systems to manage their generation, distribution, and consumption within a small geographical area. So, as you may see here in this schematic diagram, here firstly we have the main power grid, then we have a step down transformer here, and this is the PCC or point of common copying. And in this microgrid, we are having a wide variety of energy resources, starting from PV, biomass, small micro hydro generation, micro turbines. Then we have battery storage and inverter system in order to store the excess energy and also for reactive power support. Then we also have some fuel cells, diesel generators, and DFIG or wind turbines. Along with this, we have localized loads here. So this whole is known as a microgrid. So we'll see some basic features of this microgrid. Firstly, it is decentralization. So what do you mean by decentralization, anyone? Basically anything which is not centralized. So as we know previously, we had a centralized or vertical structure of electricity in our power system. So where we had some generating stations and then followed by the transmission and distribution system. But now we are undergoing restructuring of our power system, and moreover, this is what is known as decentralization. So, due to this microgrid, what we are doing is the generation is now located in the you can say close to the loads. So, what will happen is now the losses occurring in the system will decrease, which will lead to increased efficiency. Secondly, we have resilience. So resilience means in the context of microgrid, what we mean is whenever we have a fault in the grid side, these microgrids they can isolate themselves from the faulty section, and then the localized generating sources which we have in these microgrids, they can provide power to the critical loads in the microgrid, and then they can ensure uninterrupted power supply to these critical loads. So we can say this microgrid formation we can take place in case of remote areas such as let's say off-grid or remote areas or and where we need crucial loads such as in hospitals or airports or military bases. Then thirdly we have renewable integration. Obviously along with the storage we can incorporate more amount of clean, green and sustainable energy resources fourthly, coming to energy management. So, as I said, with the help of a sophisticated control system, we can control the power consumption depending upon the demand at that time, the availability of generating sources, and lastly, cost also. So, taking these factors into account, we can optimize the energy that can be used in that specific time period. The fifth feature of this microgrid is islanded mode of operation. So what this means is basically, as we discussed in the resilience point, it will disconnect from the main grid in case of a fault, and we will be supplying power to the local loads. Sixth is grid support. These microgrids, they can also follow the grid instruction so that and facilitate the grid. So what basically it means is, let's say the grid is already congested now, that is it is facing peak demand. So these microgrids, they can avoid re-injecting or peak drawing more power during those times. So in that way, they can support the grid for its operation. Next, we'll discuss about the various operating modes of these microgrids. So this microgrid, they can operate basically in first grid connected mode, that is they'll be in synchronous operation with the grid, and they can import or export the energy required according to the generation and demand that is in the microgrid. Basically what is here is in the grid connected mode, let's say we are having Pg amount of generation in that microgrid with a demand of Pd, then this will always not be equal. So the mismatch amount of energy or power will be supplied from the grid, which is equal to Pd minus Pg. What this means, whenever we are having excess of demand, that is Pd greater than Pg, we will import, and whenever there is excess of generation, we can re-inject back to the grid or export. So from this we can also earn additional revenue. The microgrids, according to that tariff at that time instant, they can get power for this extra amount of power that they are injecting into the grid. Then we have second is the islanded mode of operation. So here in case of, let's say there is a fault in the grid side, then isolate and operate on its own. So the black start mode means, as we know, the generating sources, they can be divided into two types: black start type generators and non-black start type generators. So can anyone give me example of black start type generators?
Diesel generator plants
Okay, linear. And an example of non-black start type generators?
like The micro hydro turbines.
Hydro turbines still they require a very small amount of auxiliary. They are also coming under black start basically you can say. So here we'll be having thermal. So this microgrid and also battery energy storage. So with the help of these black start resources, the microgrid can restart on its own without taking support from the main grid, and it can continue to supply power to its critical load in the black start mode. Then we have peak saving mode. So what will happen in this peak shaving mode? This is when we'll be having high demand, that is peak demand. What we will try to do here, two things we can do. Obviously, we can ask the flexible demand to consume less power, or we can switch off them, or we can re-inject power. That is with the help of batteries, we can force them to discharge during these hours in order to help for peak shaving operation. Then we have energy export mode. So when can the microgrid export energy? We'll discuss here. Obviously, when we are having our excessive generation in compared to the loads, and then we can get payments. Then lastly is demand response mode. So what is this now? Basically follow the grid signal or follow the grid. Basically we have the grid here, and we have let's say a microgrid here, PVs. Basically here at this PCC, here PCC, we can inject power according to the command from the grid. So this flexible response is known as demand response. So what we are doing, not only we are trying to manage the grid with the help of generators, we are now asking the loads also to be flexible and take part. Then coming to islanding, which was the main discussion for this week. So it refers to the condition when a section of the distribution system, such as this microgrid, it is electrically isolated from the main power grid while still generating and distributing the power locally. Basically, I had a grid here with a distributed generator with a DG, and let's say we consider here a very small microgrid, and then let's say we detected a fault here. So the breaker here, it will open to isolate this healthy part from the faulty section, this healthy microgrid part, and this DG, it can then supply power to these loads this way. So this islanding is of two types basically, intended and unintended. So intended islanding is done when we are doing it intentionally for the operation or maintenance of the system basically. So it is done firstly in case of faults, as we discussed, to increase the reliability and resiliency so that we can provide uninterrupted power supply to the local microgrid loads when the grid is having some faults. Secondly, we can also have this intended islanding when we are having, let's say, some service repair, repair and maintenance. Then also we do the intended islanding. And in this case, what happens is, in case of fault, the localized resources, they will provide power to the localized loads. Then we are what we are considered we are we can say focused on is unintended islanding, because here we this islanding is happening without our knowledge, so we need to detect this whenever it happens. So basically it is having occurring unexpectedly when we don't want it. So this can be dangerous because the workers are, let's say, repair crews when they are working here, and you have a, let's say, some workers are working here, they did not expect the power from this side, right? They were expecting power from the grid side. But what will happen in such a case is, whenever there is a islanding, the power will flow through this here, and they may get the shock. So it can happen due to various reasons. Basically, when we have incorrect relay settings, so that we'll having maloperation of the relays, or there may be communication failures, some faulty equipments, or other issues. So hence we need to have anti-islanding protection measures in order to prevent the situation. So these protection schemes, what they can do is they can detect the grid failures and immediately they can shut down this DG, so that they can off this DG, so that there is no backfeed of power, so that the workers' safety can be ensured. So here we will see in detail what are the main issues. Firstly is out of phase reclosing. So as we know, for synchronization, what we want is phase matching, and during this islanded operation, what may happen is we may reclose in such a state where the phases are not matched exactly. Then this will lead to circulating currents within the phases. Then we'll be having degradation in power quality. Obviously, when we don't have the grid, which basically is the support for voltage and frequency, then in case of a islanded system, this mismatch which you discussed, PG G may not be always equal to PD. Similarly, QG will also be not necessarily be equal to QD, and hence they can lead to voltage and frequency instability within the microgrids. Then obviously grid protection interference. So these settings which we have of the various power protection devices, they may not be may not have considered these kind of scenarios, and it may lead to their maloperations. Then we have inverter control mode switching. So as we had discussed, these microgrids, they need very sophisticated control system within them. And whenever such kind of islanding occurs, it may interfere with this inverter control modes, leading to unfavorable operation. Then this malfunction which we discussed, the relay settings. So relay circuit breakers, state settings, their operation, they may be hampered, they may be mistreated with this, due to this unintended islandings. There will be obviously damage to the equipments due to this. We can say voltage and frequency instability. There will be damage to the equipment within the grid, microgrid basically, and this threats to the personal, as we had discussed here, because there will be the personal working here. So they may be prepared for the electricity from the grid, but what may happen is there is back injection, and then they may face shock. Then after this we had the relay non-detection zone. Basically this delta P, as we had studied, so it was PD minus PG and delta Q, which was QD minus QG. So this relay, they can detect these we can say mismatch only after some some threshold. When this delta P is greater than some P threshold, then only it is able to detect the islanding situation. Similar for delta Q. Then only for these conditions only the relay can operate. Relay will operate. But if it is vice versa, if it is less than basically this region, we can say this is the PT or P threshold. This is negative times P threshold. This points basically. This is Q threshold. This is negative times Q threshold. So if only the mismatch is greater than these threshold points, then only relay will be operate or on. But if it lies in this region, that is, it is less than the mismatch is less than the threshold, then the relay is unable to detect, unable to operate. So even if there will be a mismatch, even if there is an islanding condition, then no, then if it is less than the threshold quantity, the relay cannot detect such a condition. So it this zone will represent the potential vulnerability in the system's ability to identify the islanding conditions. And it is influenced by various factors such as obviously the settings of the relay, the design. It will also very much depend upon these threshold quantities, the types of the distributed generators we are having, and the characteristics of the grid. Then we had studied in this week regarding various islanding detection techniques. Mostly they were divided into four parts: passive detection technique, active detection technique, hybrid, which is P plus A, passive plus active, and lastly communication based techniques. Basically, all the passive detection techniques, what they do is they will continuously monitor, continuously monitor the different parameters of the grid, voltage, current, and whenever they will detect that certain quantity, let's say certain quantity E is greater than its threshold value, then it will say that it will detect the island. So basically, continuously it will be comparing various electrical parameters with the threshold quantity, and whenever it sees that the parameters are exceeding the threshold quantity, it will say that the islanding has been occurred. So these various electrical parameters include voltage, frequency, impedance, phase angles, sequence components of the voltages and currents. So some of the passive islanding detection techniques based on, firstly we had frequency, that is a Rocoff rate of change of frequency. So it will continuously monitor the rate at which the grid frequency is changing, and whenever it will encounter a sudden or rapid change in frequency, then it will detect the islanding condition. Similarly, for voltage phase angle, so instead of frequency, now we'll be monitoring the voltage phase angle between the grid and the distributed generator. And whenever there is a significant difference in phase angle, it will imply a islanded condition. Hmm. The third one we had power quality. Basically, we had seen the example of voltage ripples. Because this islanding, they can introduce voltage distortion due to harmonics, and it can lead to abnormal voltage waveform shapes, and whenever such distortion is observed, we can say islanding has been detected. Similarly, we had positive sequence voltage impedance, where we'll be monitoring the impedance, and whenever there is deviation from the threshold. Similarly, all these techniques have the same operating principle, only they differ on which magnitude or which parameter they are monitoring. Then lastly, we had DSP, digital signal processing techniques, where we analyze the voltage and current waveforms continuously and draw their patterns to analyze the islanding condition. Nextly, we also saw superimposed negative impedance based islanding detection techniques. So we'll see this in detail. Basically, first you can see here we will acquire the voltage and current signal as we had seen in the previous week. So we'll receive the samples, right, at the sampling frequency. So what we'll be having, we will be having certain samples, and using these samples, we'll calculate the magnitude and angle, basically the phasor, we can say phasor quantities. And once we have the phasor quantities, then we will be calculating, basically these will be the phase voltages, that is VA, VB, VC. Then we will have some transformation matrix to convert them into sequence component. Similarly, we will be also having it for the currents. So from this also, using the transformation matrix, we will get the sequence components, and then these ratios will give us the sequence impedance. So once we have this, basically K, Z2, we can say these are sequence. Z2 implies it is negative sequence, right? So at each point we are trying to find the difference between the two consecutive. We will get series of Z as we have series of voltage and current here, and if their difference is rate, basically rate, because we are dividing by time here, if their rate is greater than certain threshold here, then we can say we have islanding condition here. So this is Z post, that is at, let's say, current at kth instant, and Z pre, that was its previous instant k minus 1, divided by this time interval, we can say basically this time interval, we will get this rate of change of superimposed negative impedance. And if it is greater than the threshold, then we can say we have a islanding condition here. Then coming to the active island detection techniques, we had two basically methods. Firstly was the signal injection based method. First, then second was the positive feedback based method. So in the injection, obviously by the name as it suggests, the signal injection based techniques will be injecting certain external signals like negative sequence signals, or we can say pulse signals through the inverter controls. And by injecting these signals, we'll observe the behavior at the PCC. And due to this injected estimate, due to this disturbance signal. Similarly, in positive feedback based technique, what we have is these we have electrical quantities such as, we can say, frequency, voltage deviation, phase angle, etc. They will be given as feedback signals to the inverters, and this feedback is basically positive feedback, due to which it will be we can say derived into a unstable condition, but it will be controlled. Then obviously to this basically passive ones, they had certain disadvantages. Can anyone recall what were the disadvantages of these passive techniques? What were the issues with this passive islanding detection techniques? First one is it had large non-detection zone, basically, which we had seen. And in active, what was the issue? In the active method, since we were injecting signals back, so they were leading to power quality issues. So in order to overcome these disadvantages, we went for hybrid. detection techniques, where first continuously we will be using the passive techniques to detect the islanding condition. If the islanding detection is not detected by the passive, then only we will be going for active. By this way, we can we can say minimize the spark quality issues. Lastly, we had communication based techniques. Basically, whenever there will be a loss of communication between, whenever there is loss of communication, then it will detect the islanded condition. But these are very costly methods. Then we had a comparison tables of the various types of islanded detection techniques. Firstly, these these were passive detection techniques. So, although they were cost effective and they did not have any power quality issues, but they had large non-detection zone. So it may so happen that we may not be able to detect islanded condition under certain mismatch condition, or when we can say less active or reactive or mismatch condition, then we cannot detect the islanding condition in these kind of techniques. Then in the signal processing based methods, they had lower non-detection zones compared to the passive methods, but they required high processing requirements. Then we had the latest AI based techniques. Here they also had lower non-detection zones. They did not have any power quality issues, but they are difficult to practical because in order for these methods to work, we need first huge amount of data to train them, train these models basically, and hence we can say till now it has not been practical to use these techniques for islanding detection. Then moving on, in the active methods, we had current injection based techniques where basically we change this phase quantities into DQ frame, direct and quadrature axis frames. So the transfer matrices, and in these D and Q axis, D and Q axis, we had external signal injection, and from then we used to monitor whether we are having islanding condition or not. So these again have negligible non-detection tone, but since again we are injecting external signals here, they may lead to power quality issues. And also we had seen positive feedback techniques. They may drive the distributed energy resources into unstable mode of operation. Because basically, if we have negative feedback, then it stabilizes the system, but a positive feedback will always drive the system into unstable mode. Then coming up, we discussed the protection issues that are occurring due to these distributed energy resources present in the microgrid. So we studied four types of protection issues. Firstly, the dynamics in level of fault currents. Then we had bidirectional fault current, fault stripping, and lastly blinding of protection. So we'll see one by one. So basically, this is the islanded mode, and this is so that because here the circuit breaker is open, and here we have a grid connected mode. So whenever you can see the fault current, we have three sources here. First one is the grid, second one is this generator G1, third one is we have generator G2. Whenever we have a fault here, These three sources combinedly will contribute to the fault current. You can see here IF equal to IGF, which is the main grid feeding current, then fault current from the source G1 and G2. But whenever we have islanded mode of operation, then this fault current is only fed by these two sources. So what will happen is, let's say if we did not consider the islanding mode of operation and set the relay setting as, let's say we had relay overcurrent relay, basically let's say 5 amps. So previously we had this as 3, and let's say this was 1, and this was, let's say this is 3.5, and this is 2. Then we can say the fault current here was 356.5, which is greater than 5, so that the relay will operate. But in this case, the fault current will only be equal to 3, which is less than the overcurrent setting. So what will happen is, even if there is a fault, the relay will not operate. So we'll be not able to isolate the faulty section due to the incorrect relay settings. So basically this was the first issue here. Moving on, the second issue that we are facing is the case of bidirectional fault current. So here again, let's say we had a fault F1 in the first condition. So here we have two sources. This is the grid, we can say grid, and then we have this generator. So what will happen is, when there is a fault here, the fault current seen by this generator or relay, sorry, this relay is in this direction, and it will trip so as to remove this part. But let's say there is a fault at this PCC, then we have that grid is feeding to this fault, and this generator, distributed generator, it can also feed to the fault. So what will happen is, we need to also detect this kind of fault and trip this. But traditionally in this distribution system, what we are having is, mostly we are having non-directional, because mostly we are having overcurrent relays. So these kind of relays, they are not able to detect such kind of faults. Then moving on, we had false stripping. So what will happen here, we'll see. Let's say we had two feeders here, feeder 1 and feeder 2, and there is a fault in feeder 2. So under ideal condition, what should happen? Only F2 should isolate, right? F2 should isolate and F1 should be in operating condition, because it is a healthy feeder. What will happen is, when we have a fault here, this generator will start to feed this fault current, and this being a non-directional relay, it will also trip. So whenever this will trip here, that means we are isolating the healthy feeder also, which was not the ideal operation. We are isolating this feeder F1 also, which will hamper this load, which was in a healthy feeder, but still, due to the small operation of this relay, this healthy feeder was also isolated. Then last we had blinding of protection. Basically what happened here, because, so here let's say we had a fault here. So The I fault was I capital G times fault plus I GF. When this is when we have grid connected here. So what will happen here is the amount of fault current I fault that will reduce here. So what may happen is IG capital F. So in case of a fault, this relay may not be able to detect because certain quantity of fault current is also being supplied by this generator. So basically we can say this relay will be blinded. It will not be able to see the current. So it will not be seeing the fault. So okay, then we'll move to the Q&A. So the first question is open. Determine the superimposed negative sequence impedance at the PCC where the magnitude of the negative sequence impedance before and after islanding is estimated to be 50 ohms and 70 ohms respectively. So you may type the answers in the chat box or you may also unmute as you wish. Basically, this is here what we are asking is delta Z2. So anyone? What will be the superimposed negative sequence impedance? It was Z2 post minus Z2 pre. So I think now you can tell what will be this magnitude.
It's 20, ma'am.
20. Anyone else with any different answer? Okay, this will be 20 only because here we had after as 70 volts. So this is 20. Then moving to the next question. The disadvantage of the current injection based islanding detection scheme. Current injection. Basically, we had seen this in the active mode, sorry, active islanding detection scheme. So, what is its disadvantage? Anyone?
Power quality degrades, man.
Okay, we got one power quality degrade. Anyone else? So, in this active mode, we had current injection and we had another method. What was it? Anyone? One was current injection based method, other one was positive feedback method, right? So, what was the disadvantages of these? Basically, we moved from passive to active because passive had higher non-detection zone So this will obviously not be the answer because in active mode we are moving to lower non-detection zone. So with this we can discard this option. So this option will also go from here. Then we had power quality degradation and we had unstable mode of operation. So this we got in case of
Power quality degrades.
we got another power quality degrades. Thank you. So this we had seen was the case of positive feedback and current injection method. Here we got due to power quality issues due to current injection methods. So the right answer is power quality degrades as two of you have suggested. Next we have the Q-axis current injection causes sinusoidal component to exist in dash during the dielectric condition. So this injection of IQ will lead to sinusoidal component in which parameter? Is it the D-axis voltage, the Q-axis voltage, the frequency, or the voltage? Anyone?
It's voltage, madam.
Sorry, again,
It's frequency, madam.
frequency.
Frequency during this. Yes, madam.
Okay. Anyone else? Anyone else would like to take take up the question? So, Mr. Guru Mohan Prasad sir, so can you like tell us why do you think it is frequency?
Uh, While hearing classes, I remember that this
Okay,
frequency, and it is.
true. Okay, true sir. It will be frequency only. So basically, what happens is here when we have IQ. So in the transformation matrix, basically when we have, so we'll be having some kind of formula which is like if you remember they'll be having in sine cosine components, and there you will be having terms such as if you recall sine a plus b sine or sine c plus d and sine c minus d. So there what we do, we'll be having the components, let's say sine c plus d. So there what we'll be having is the operation over these omegas or the frequencies. So due to this, we'll get distortion in the frequencies. Basically, they may be addition of the two frequencies, or there may be subtraction. So these type of harmonics will get due to this current injection. So as rightly said, so this will be frequency. Then next we have the penetration of the distributed energy resources. It will change the magnitude of fault current, the direction of fault current, magnitude and direction of fault current, or none of the above.
It's magnitude and direction of fault current.
Okay, we got magnitude and direction. Anyone else? I think we saw it in the protection issues for the when we are considering this distributed energy resources. So there we saw that it can alter the magnitude of fault current because we'll be having extra sources in the form of DRs who will be feeding the fault current. So we'll be getting extra sources to feed the fault. Then obviously they are bidirectional in nature. We had seen due to which the traditional overcurrent relays they are not able to detect. So they will also affect, we can say, the direction of fault current, and hence the correct answer is they'll be changing both the magnitude and direction of fault current. The next question is a nice one. So it is, if the overvoltage relay trips, then what does it imply? A positive active power mismatch, negative active power mismatch, positive reactive power mismatch, or negative reactive power mismatch?
Positive active power, reactive power mismatch.
Positive reactive power mismatch, we got one. Anyone else? Anyone else? Just try to recall the non-detection zone of the relays that we were studying. There we had in the axis. Anyone else? So here basically, if you remember, we had delta P here, we had delta Q here. So in case of positive active power mismatch, we got one B. Anyone else? So the positive mismatch would imply PD is greater than PG. In this side, when we have negative delta P, so here it will mean PD less than PG. Here we have positive delta Q implying QD greater than QG. Similarly, for negative delta Q, we'll be having QD greater than QG. So, what we can say here, whenever the demand is greater than the generation, such kind of situation will lead to under voltages. Whenever we have excessive generation, these will lead to over voltages. Whenever we have excessive Q demand, we'll be having under frequency, and whenever we have QG, reactive excess. If someone wants to speak,
Negative
Madam,
real
you PD is greater than PG, then it is frequency will come there, not voltage.
we'll discuss that. someone else was answering. Nivarshan KR.
So, negative real power.
Negative active power, you mean?
Madam, actually, whenever demand production is more, then frequency will decrease, madam. Why it is reverse way?
I am coming to that. So basically, whenever we have QD less than QG, then we'll be having over frequency. So I know all of you are concerned about the fact that since we are very much aware of PF and QV, but can you all recall that this was under certain assumptions? This decoupling, when we went, it was not inherently in the equations. We took some assumptions to decouple these equations. Because if you inherently remember the P and Q injection, it is P is summation. If I say Pi, it is Vi, Vk, Yik, cos of delta I minus delta K minus theta K. Am I right? We had this for P, and for Q we had the same with sine Vi, Vk, Yik, sine. So here we can see for the active power equation we have both voltage, magnitude and angle, and in reactive power equations also we have both magnitude and angle. But when we took some practical assumptions, then we got these decoupling. But can anyone remember what were those practical assumptions that we took here?
Madam, as per the literature, we have known that whenever load is increased, then frequency drops. It's the
Yeah,
case with inputs also.
that was the case
Whenever,
for transmission system, sir.
yes, madam, yes.
So in the transmission system, we had the, we can say, advantage where firstly, if you remember, the R by X ratio, it is very small.
Yes, madam, yes.
So these decoupling, if you remember fast decoupled load flow, when we went from Newton Raphson to decoupled and fast decoupled load flow, so according to these, we neglected some B term here. So that was for transmission system only. When you study for distribution system power flow methods, distribution system power flow, such kind of assumptions we can't take. We're unfortunate because for distribution system, the R by X ratio, it is, we can say, not small. They are comparable. So why this happens? Can anyone take a guess why this R by X ratio we are getting very small in transmission system, but for distribution we have comparable?
The conductors used in distribution systems are very small conductors. That area of cross section is very low, and for transmission we generally use fans and
Because of
different.
depending on the rating, and secondly the length of
Yeah.
feeders if also you will consider. So due to these conductor characteristics, if you see any data sheet also for transmission and distribution system, so for distribution system we can't actually decouple these, we can say, these equations. For a distribution system, I'll say there is a strong coupling between all of these P, Q, V and F. But in transmission system, we had the can say advantage, we enjoyed the advantage of PF and QV coupling. But in distribution system, they all are intertwined. We can't basically ignore one such thing. So this is the case due to which we are getting such relation. So basically here we asked for over voltage relay. So this was the case of over voltage relay, which means the we had excessive generation, which implies a negative active power mismatch. So I hope it was clear. So from here
But
we
ma'am,
can.
in this question, it is not written whether it is transmission or whether it is
Sir,
distribution.
when we are talking about microgrids localized, so by default, when we are coming to the low voltage levels, so it is understood that in this whole week, basically, we were talking about the distribution system. Okay. Then we have a question here, numerical, small numerical. So if a microgrid has a 300 kVA load at a power factor of 0.9 and a solar PV generation of 300 kilowatt, and basically if you have a solar, we also will be having an inverter, and that inverter capacity is given as 330 MVA, then find the active power imbalance in the islanding condition. So please just, I'll give 2 minutes to try. So anyone?
30 kilowatts, ma'am.
30 plus 30?
Yes, ma'am. Yes, 30 kilowatts.
Okay, I got 1 plus 30. Anyone else? Okay, anyone else here? Okay, Guru Mohana sir, can you help me with here how you proceeded for the solution? Basically, we had
Ma'am,
SD.
actually, active power load, active power is 300 kVA and 0.9 PF, that is 270 kilowatts,
Hmm.
270 kilowatts, and the generation capacity is 300 kilowatts. So that I have come to the conclusion that it's a difference of 30 kilowatts.
Uh,
That's it.
okay, I will just ask you to remind whether the mismatch is PD minus PG or PG minus PD.
Is PG minus PD, I think.
No, sir, it is PD minus PG. If you can see, this mismatch is okay. So we had, you remember, all of you must be remembering this power triangle basically. So from here, you can get P as S cos phi, and this cos phi is your power factor, which is given as zero point 0.9. So basically 300 times zero point 0.9, which you will be giving us 20, 70, 270, kilowatt, and then we had Pg as 300 kilowatt. So from here we can calculate delta P equals to Pd minus Pg, which is minus 30 kilowatt. So it is minus 30 kilowatt. So can anyone tell me, under this condition, negative mismatch, which relay will be tripping? We are getting
Over
a
voltage.
over voltage. Yeah, as correctly stated, we will have over voltage relay operation. Then for the next question, the same question, but now you have to calculate the reactive power mismatch. Microgrid is having 300 kV load at 0.9 power factor and a 300 kilowatt solar generation capacity. The solar generation is connected to an inverter. Find the reactive power imbalance when the islanding condition is present. Anyone? What is in class? Similarly, as we calculated active power, you may proceed for reactive power. I think someone was looking for you. Okay. So basically, let me ask you here. If we have a like solar PV, we know it will be able to generate only the active power, and its inverter, it will help to generate the reactive power. So a PV plus inverter, they will give the PQ characteristics just like a, we can say, conventional thermal generator, that is circular, right? Where this is, let's say, P max. So this will be represented by P square plus Q square equal to S square. So the P here can vary from 0 to P max, that is the maximum rating of this PV, and depending upon this P, the inverter will be able to generate the Q. So you may use these for the PV plus inverter combined system. So basically, as we had calculated previously, so what will be QD? Anyone?
S into sine phi.
Yeah, correct. So S into sine phi. So in place of S, what we'll put here? What is the S here? S demand.
300.
Okay. So we put here 300. Then sine. We know cos phi was 0.9. So phi is cos inverse times 0.9. So using this, what we get? Anyone?
30 degree.
No. I am asking for whole.
Okay.
130.7, ma'am.
130.7. Anyone else? We got 130.7. If you do this 300 times sine of cos inverse 0.9, okay, you will be getting this 130.7, and its unit will be kVR. Then moving on to Qg. What will be Qg? The relation, anyone? This is the capability curve, right? So from here,
Q equal to square root of S minus P.
yeah. So here what will be getting? Square root of Hg square minus Pg square. So what we have Hg, I have given here as 330, right? So it will be 330 square minus, what is Pg? 300.
The units are given as a 330 MVA, ma'am.
Oh, sorry, it's kVA. My bad. Take it as kVA.
In previous question also it is MVA, ma'am. Though it is
Okay,
not
okay.
used in previous, but it is.
Because I had the same question. Okay, so here what we'll be getting? 330 square. And so what will this give? 137.47 kVR. Basically, this will be then delta Q as QD minus QG, which will give us minus times 6.7 kVr. So is it clear?
Yes.
Thank you. Okay. Then moving on, which of the following is a disadvantage for a rock off, basically rate of change of frequency, passive islanding detection technique? Determination of threshold, large non-detection zone, it will vary with load and generation inertia, or all of the above.
So large and DZ.
Okay, we got one large and diesel. Anyone else? Rock off. Basically rate of change of frequency. Basically, for all the passive ironic detection techniques, both of these are a disadvantage because, as you may recall, for the passive ironic technique, what we were doing, we were continuously monitoring or observing certain parameter, let's say voltage, phase angle, frequency, or something, and then we were comparing it with a threshold. So, what is this threshold is very crucial. The selection of this threshold will determine if it is in detection zone or not. Let's say we have a threshold of 5, so it is very crucial because just within this short, we can say, range, we'll may get islanding detection or not. So what will be this 5, whether it will be dot 5, whether it will be 5.1 or something. So determination of this threshold is a very crucial in passive detection techniques. Similarly, we had also seen they have large non-detection zones. That is, for lower mismatches, they are not able to detect the islandings for lower delta P and delta Q. And additionally, since we have a frequency here, so this frequency will vary as the load varies and also as the, we can say, the H of the generator varies. So these two will lead to change in frequency. So we may not be able to distinguish if this rate of change of frequency we are getting due to islanding condition or due to this system condition. Due to this load variation or generation variation, then also we may get some delta F. So sometimes there may be maloperation because it may not be islanding condition, it may be a load variation, but what the threshold, if it crosses the threshold, then we may falsely take it as a islanded condition. So the right answer here it is all of these are the disadvantage for rock off. So the next question is, a positive superimposed negative impedance will imply positive active power mismatch, negative active power mismatch, zero active power mismatch, or you can't say with this information. Anyone here? Positive superimposed negative impedance. So what do you mean by first this statement only? What do you infer from this statement?
Positive sequence tennis will be taken for considering this
Is
superimposition.
positive sequence impedance or negative sequence impedance? A
Negative
positive
sequence impedance, ma'am.
negative, because we are telling a superimposed negative impedance and it is positive. So what was superimposed negative impedance? It was, if you remember, delta Z.
It is difference in between pre and post fault impedance. Pre
Ah,
and post fault negative impedance.
pre and it is the vice versa. It is post minus pre. If you remember, I'll just take you. It was delta Z2 was post minus pre. So I am telling that this negative superimposed impedance is positive. So what do we mean mathematically is basically that this delta Z2, which is Z2 post minus Z2 pre, their difference is positive, implies it is greater than 0, right? So I hope this statement is clear now. A positive superimposed negative impedance means this condition basically. So such a condition, what is going, it is implying? Is it implying a positive active power mismatch, negative active power mismatch, 0, or this we cannot say with this amount of information? Anyone?
Maybe positive active power mismatch.
Okay, we got one positive active power mismatch. Anyone?
It A answer, ma'am.
Okay, we got another positive active power mismatch. So can anyone help me, like how you came to this that it will be positive active power mismatch?
Because the difference is greater than 0, so greater than 0 implies positive.
Hmm.
That's why I predict it's a positive active power mismatch.
Okay. Anyone else? Basically, we are telling, as I said, we are post is greater than pre. So what it will imply that Z was V2 post is greater than V2 pre. So if let's say your V2 pre was 1 per unit and you got V2 post as zero point 0.1, so what will it imply? An increase in voltage will imply over demand or over generation. increase in voltage. What does it tell you about the system loading condition?
It V2 post is 1.1.
I am supposing, I am not telling it is this value. I'm trying to tell this with the example.
So this is over generation.
This is over generation because we are getting over voltages. This is not kind of over demand, we are getting over generation. So if you remember, delta P was PD minus PG. So over generation means your P generated is greater than P demand, right? So what this will mean then? The mismatch will be, it will be negative, right?
Negative.
So we can deduce here that if we have a positive superimposed negative impedance, it is implying a negative active power mismatch. Okay. Then the next question. The limitation of AI based landing detection technique is it will be have power quality issues, it has large non-detection zone, it is difficult for practical implementation, or it will drive the system into unstable mode.
What is AI?
Artificial intelligence. We got one C. So anyone else?
I think it is D, ma'am.
D. We got another D. So obviously these issues were mostly for active techniques we had seen because we are externally injecting signals. This we had seen for most passive techniques like your rock off, and this also we had seen in case of positive feedback active technique. So here the correct answer is basically, although this AI based island detection technique, they will be having lower non-detection zone, they won't be having power quality issues, but they are right now difficult for practical implementation because that kind of data and that level of communication system has not been established in current context. Okay, any doubts if anyone? Actually, if not, I have one doubt. So in this question, we saw that since PV does not have the capability to uh, absorb or inject reactive power, we need to have an inverter. So how do we decide this size of inverter? So let's say you have a 100 kilowatt PV solar panel with you. Then firstly, why do you need an inverter? That obviously we answered for Q support, but then if you are going for inverter, how will you determine its rating? Anyone?
So power factor is normally 0.8 cos phi.
Hmm.
So now from there, cos phi is 0.8, we can calculate sin phi, and then from there we can calculate the KVR rating.
Okay, here basically this we need for Q support, or basically this power factor support. So what we have a standard that the IEEE is suggesting, because as a consumer, are you really concerned about your Q consumption limits or power factor limits? We are not, because it is not directly a issue to us, but it is matter of concern to the grid owners. So they try to impose regulation. Otherwise, without this, no one would like to bear this extra cost of getting an inverter installed, because it is not directly beneficial to them. So we have standards, those who impose that. If firstly, there are variations to it, that if you have this amount of P, then either you have to maintain between 0.95 lead to zero point 0.9 lag at PCC, or certain standards they suggest that you must be able to provide support of 42% of your P max as Q, which implies that if I take a 100 kilowatt PV and install a 100 MVA inverter, then it will imply that so such an inverter at P max, will you be having any Q capability? No, the Q is 0 here. But what it is suggested, that your inverter size should be such that whenever you are at P max, you must be having a margin of at least 0.44 times P max as your Q. Okay, so if you do the calculations, basically it comes out that if you have a PV with Pmax rating Pmax, then your inverter S rating should be 1.1 times of 1.1 times of Pmax in order to satisfy this requirement, that at maximum power from your solar you must be having some reactive power margin or with you. So due to this only we are going for inverters. Otherwise, if this standard is not imposed upon us, I think no one will be having this, and it will lead to
Ma'am, generally that generator has a 0.8 power factor lag, na? So in this also, inverter also, we have to see lag or lead.
both, sir, both lag and lead. As I said, no, 0.95 lead to zero point 0.9 lag. So
But
it is now
generators are operating at point 0.8 lag, na ma'am?
not always. They like get a range within which they have to maintain, and not always lag. They can be also requested for lead operation, but it is very less. You can see 0.95 lead only they're expected. So this is for DRs, and generators are from zero point 0.9 lead to point like zero point 0.9 lag, I think. So basically, due to this, we have different capability curves. So this is one type of inverter. If you have, some may maintain their PQ, we can say, as constant power factor mode. So then if they will be having linear relation, basically this will be constant power factor mode. So depending upon various modes of operation, you'll be getting this relation between PG and QG. Basically, PG, it is not controllable for most renewable type of plants. So according this relation, whether it is in constant power factor mode or this full circle mode, you can calculate the amount of reactive power. Such kind of variations you get. So anyone else? We have time if anyone wants to. And Anupam sir, actually, I thought about your problem regarding that power market issue basically. So what I guessed, because I am not aware that till now anyone from the distribution side has tried to bid in the power exchange, but since you are you are in the distribution side, right? Like you are connected with the distribution system feeder.
Yes, yes, yes.
Huh. So when you will be injecting power to the transmission system, it has to flow through your distribution system, right? Had it been the case that you were connected to the transmission system, then you did not use the distribution system resources. But now, since you are in the distribution system, you need their clearance also from the discount. Are you getting my point, sir? So,
Yes, yes.
that for that reason only, I think they are suggesting that you take some permission from your distribution system to use their resources, because through that only you will be supplying power to the transmission system, right? So maybe you need to first see the rules of your discoms and get some clearance from them. And if you attach that to the power exchange, I think they'll accept you.
Okay.
Okay. Anyone else? Okay. And this was basically for this week. We started from microgrid, then we saw different modes of operation, islanding, non-islanding. Then we detected the islanding detection techniques. Then we saw the issues with the smart grid protection due to the addition of these distributed energy resources. And in the next week, I think again we'll continue with these issues. And okay, I think if anyone does not have any doubt, we'll close this session. And you all may join for the next session. I think you have from 6 to 8, right? And I hope the questions were not repeated. We took care of that. So if you want, if you may join for the next session that is being going to be held from 6 to 8.
Thank you, ma'am.
Thank you. Thank you everyone for joining.